This is problem 3.1. Let's read through it. Consider the following problem to model oxygen-carrying species and reaction inside a cell. Determine a model for the system based on the information provided. What other key assumptions have you made? Assume the following. The oxygen-carrying species is level B with concentration C sub B in units of moles per liter in the cell. Species B diffuses into the cell at a total molar rate of D sub B times A times the quantity Cb naught minus Cb, and again moles per second are the units. Species B is converted to species C inside the cell at a total molar rate of Vm times a bunch of stuff, Cb over K plus Cb, moles per second for that rate. Species C diffuses out of the cell at a total molar rate of D sub C A, quantity C sub C minus C sub C naught of T, moles per second. The effective cell volume is V, it's a mistake. Cb and Cc are the molar concentrations inside the cell of B and C at time t respectively. Cb naught and Cc naught are the molar concentration of B and C outside the cell at time t respectively. There's even a little picture here showing diffusion across a cell wall, the volume, concentrations that B is converted to C, the reaction rate. In that case, it shows that the total molar rate is Vm. That's not consistent. That should be V there, not Vm. And this is the rate for C leaving the cell. So, first thing we're going to do is go over here and start to write down some of the things we know about this problem. And let's see if it will focus. It's got to focus better than that. That's sort of terrible. It's not focusing at all. Let me see what is going on. There we go. Maybe that'll get into focus. 3.1. So we have the cell. We have stuff going in. It's diffusing, so it could go out. We'll draw it going in this way. V inside the cell. We have two species, B and C inside the cell. We have a reaction. We have C leaving the cell, although C could come back in. Outside the cell, the concentrations are C sub B naught and C sub C naught. Inside the cell, it's C sub B and C sub C. If we want to, we can make these functions of time. I think that's how they're denoted in the problem. So we have all these different species. We know the volume here. We don't know the volume outside the cell. So we're not going to have to model these external species. We have no idea what the volume is, so we can't figure out anything about accumulation rates overall for these species. But we can model the cell itself. So let's write down, since we have one volume and two species, we're going to have two balances. One is going to be for B, and one's going to be for C. Balance on B and C inside cell. We're assuming, the biggest thing we're assuming, well mixed, which is not a very good assumption necessarily for cells, but it's a start. And we're going to say constant physical properties. So things like the reaction rate coefficient, diffusion rate coefficients, those things won't change under this model. First, we have to get our accumulation rates. So we know the volume of the cell is V. For species B,
it's V times dCB dt. And for species C, it's V times dCC dt. And that comes from looking at the total amount of B and C inside the cell. If you remember, we can do the concentration of B times volume. That's the total number of moles inside the cell. If we take a time derivative of that, you end up getting V dCB dt plus CB dV dt. So I guess one of our other assumptions should be constant volume, which again is not necessarily a great one for the cell. We always assume the volume is constant for these. It goes to 0, so we only end up with the accumulation rate of V times the rate of change. So we have to figure out the rates that go on the right-hand side of these two equations now. For species B, we know it enters the cell with a diffusion rate. And that diffusion rate was given in the problem. The total diffusion rate is d sub b a times c sub b naught minus c sub b of t. Now what else is happening to B? Well, it's coming in with that rate, but it's converting from B to C. And we know the total reaction rate is given there as an expression. I think that total reaction rate should be, it's actually, since we're converting B, we're consuming B. So it's going to be a negative V CB of T over K plus CB of T. This has moles, units of moles per second. This has units of moles per second. This is moles per liter second, but this is liters, so the volumes cancel. And we get moles per second. So this balance should be good. Let's do C. Every time we react one molecule of B, we create a molecule of C. So the reaction rate there is going to be V C sub B of T K plus C sub B of T. The total reaction rate does not change. In the first balance, B is being consumed, so it's a negative value. Here, we can even write a positive here. We're producing C, so the same rate produces 1 mole of C, so it's a positive value. But C then leaves the volume, so let's write a negative sign with a diffusion rate for C, which was d sub C A C sub C of T minus C sub C naught of T, I believe. So this is a different diffusion rate because it has a different diffusion coefficient. And depending on the difference here, the concentration of C inside the cell should be greater than that outside the cell. So this number is the value that pushes C, basically drives it across the cell wall, depending on how much area, effective area, the cell exposes. And the diffusion rate coefficient, we're going to have that rate in moles per second leaving the cell. The same way we have a different diffusion coefficient, or d sub b. So this model depends on us fitting parameters for the effective volume of the cell, diffusion coefficients for B and C, reaction rate coefficients for K, assuming this reaction rate model is accurate. So we've come up with this balance. We should probably go ahead and put a box around our solution and call it a day. Not too bad, and it's a little bit messy. Could probably neaten it up a little bit, but in general, it's just two different equations because we have two species in one volume.